Hello and welcome back to another lecture on this NPTEL online course on advanced plasticity of solid continua. Today we will be talking about rate independent plasticity and a little bit of introduction to convex analysis that informs certain basic aspects of rate independent plasticity. We will motivate why we need convex analysis in lieu of the present way of teaching the subject purely based on certain ad hoc assumptions. So let us start. So let us first try to motivate a few things about why we need convex analysis. See, the important thing with this convex analysis approach to plasticity is that it offers a variational structure. That itself says a lot. The reason why elasticity is such an important and well entrenched area in mechanics of solids is because you can solve elasticity problems using a strictly variational structure. But the classical plasticity, if you look at it, we will discuss it, but it really doesn't depend much on the variational structure, and therefore there is a problem. Basically it finally turns out that it becomes a jumble or a clutter of certain ad hoc rules, and to a curious mind it creates difficulties. So we wish to actually avoid that sort of a loophole or difficulty and try to do it in a variational way. To appreciate this point even better, we should therefore take a look at how the classical plasticity in the rate independent case works in practice. Okay, so we should do that first. So we have already talked about the yield surface, but in discussing classical plasticity we also need what is called a flow rule and a set of consistency conditions, okay, as well as certain additional conditions called the Kuhn-Tucker conditions. So we will discuss them now. So let us first talk about the flow rule. We already know that there is a yield surface. There is an yield set, the interior of which is strictly elastic. Okay, so now the flow rule is a relationship between the deviatoric stress, which essentially drives incompressible plasticity, and the strain rate, the plastic strain rate. And this relationship is captured here through this. Okay, so the ratio of the deviatoric stress tensor to its magnitude or modulus or norm, whatever, all are the same things, is equal to the ratio of the plastic strain rate to its norm. Both are the same. That means we can say that if I call n by np the tensorial, a generalization of a vector direction, it is the tensorial direction of the plastic flow. Okay, so np is called the plastic flow direction. But remember that np is a tensor, it is basically a matrix. Okay, so you have to generalize the notion of a direction here to a matrix valued direction. So we see that this hypothesis is of great importance in classical plasticity, especially in the rate independent case, and this is called the co-directionality hypothesis. Okay, so this is the co-directionality of the deviatoric stress with the plastic strain rate. Okay, as I said, np is called the flow direction. Now if we write by way of a constitutive relation this deviatoric stress as a function of the plastic strain rate and alpha, which is the internal variable depicting hardening. Okay, so let us call alpha as the hardening variable. Then essentially what we see is that because epsilon p dot is partly decided by the NP, the plastic flow direction, I can write in principle this sigma 0 as a function of the plastic flow direction NP itself. Okay. But I need an extra equation to determine my alpha, the hardening variable. So, this equation is typically in this form, another ordinary differential equation, which is alpha dots is equal to some chi, a function of the plastic strain rate, which is epsilon p dot, and alpha itself. Okay. So, this equation is called the hardening equation. All right. Now, so we understand slowly, we will see how all this unfolds. In many cases, we need to actually at some stage relate this hardening variable alpha with the plastic strain rate. Otherwise, the evolution of the alpha, the hardening variable, will be happening in a completely independent way with respect to the plastic strain rate, and you will be getting wrong results. This is exactly what this equation does. This is exactly what this hardening equation does, but there is a simpler form of this hardening equation. I have not yet told you exactly what the form of chi will be, but the simplest form for this is that we just say that alpha dot is nothing but the norm or the modulus of, or the magnitude of epsilon p dot, the plastic strain rate, which has to be greater than or equal to 0. Okay, so this is an initial value problem. You can start from alpha equal to 0 at t equal to 0 and then integrate this. So, you see this is a direct relationship between the plastic strain rate and alpha dot. You also remember that in this case, because we are talking of alpha dot equal to modulus of epsilon p dot, this means that alpha now is a scalar variable, because modulus of epsilon p dot is also scalar, right. So, we can actually define the accumulated plastic strain, which is basically EP, the integral of epsilon p dot, modulus of epsilon p dot with respect to time from 0 to small t, the current time. This is called the accumulated plastic strain, and that is nothing but the hardening variable alpha. You can clearly see this by integrating this equation, you see. So, this is essentially the essential prescription for our hardening. Now, also let us take a look at the strict dissipativity in plastic flow. So, the strict dissipation, suppose there is no hardening, right. In that case, it is simple. So, in that case, the strict dissipation means that sigma 0 inner product with epsilon p dot gives you the dissipation, right. But it may be basically because epsilon p dot is also related to hardening, as we saw in the last slide. Therefore, we can include hardening also here, and we can in general say that sigma 0, which is basically a function of NP and alpha. NP is the flow direction, plastic flow direction. Now, epsilon p dot, you remember, because epsilon p dot can be written as this NP, plastic flow direction, times the magnitude of epsilon p dot, right, because the definition of epsilon p dot was this, epsilon NP was this, NP was epsilon p dot divided by modulus of epsilon p dot, right. So therefore, this is greater than or equal to 0. Now, you see that if I take out this term, this gives a scalar quantity, right. So, sigma 0 inner product with the plastic flow direction tensor. If I take the inner product of the two, it gives the dissipation per unit epsilon p dot's modulus. So, per unit magnitude of the plastic strain rate, the dissipation that occurs has a special name. It is called the flow resistance Y. So, it is defined as sigma 0 inner product with NP, which definitely is greater than 0 if the plastic flow is occurring. So, by co-directionality of deviatoric stress with the plastic strain rate, we can also say that the modulus of sigma 0 is nothing but the inner product of sigma 0 with the plastic flow direction. But this already we have called by the flow resistance Y. So, we can say therefore that Y is a function of NP, which is the plastic flow direction, and alpha, the hardening variable, if they are present. Right. So, I can therefore say that sigma 0 itself during plastic flow will be nothing but the scalar flow resistance times NP, right. NP is the tensor, Y is the scalar. Now, and D, therefore, the dissipation can be written as this flow resistance times the magnitude of the plastic strain rate. Now, there is also an extra assumption of strong isotropy in classical plasticity. That means we often assume that this flow resistance is independent of NP, right, the flow direction. That means irrespective of where the plastic flow is, which direction plastic flow is occurring, Y is always independent of that, and therefore Y only is a function of the hardening variable alpha. All right. Now, this also should remind you about one aspect that we have discussed already, that plasticity should be looked upon as a constraint on the elastic response, at least in the rate independent case. What kind of a constraint? That means whenever the modulus of sigma 0 is less than the flow resistance Y, right, that it means that basically the plastic flow is not occurring, and essentially if it is strictly less than Y, then plastic flow will not be occurring, because epsilon p dot will be 0, right. So, the flow direction, plastic flow direction NP will be basically nothing, 0 essentially. Okay, so, but when modulus of sigma 0 is equal to Y, that is possible, and then plastic flow will start occurring, and therefore plastic flow constrains the elastic response such that this modulus of the deviatoric stress can never exceed the flow resistance Y. Alright, it is a constraint. So, plastic flow should be thought of as a constraint on the elastic response of solids. Correct, as we have already said that for purely elastic response we have the modulus of sigma 0 less than Y alpha, right, which is the no flow condition. Okay, so let us now take a look at these additional conditions that we need in rate independent plasticity, provided we take up the classical route. Okay, these are the consistency condition and the Kuhn-Tucker conditions. All right. So, you remember the yield condition was given by the function f sigma less than equal to 0. F sigma equals 0 is the yield surface, right. So, epsilon p dot equal to the 0 tensor. If it is epsilon p dot is 0, that is the 0 tensor, then the response is elastic, which implies, what will it imply? Either f is strictly less than 0, or it may imply something else, that f may be equal to 0, that is the solution is still on the yield surface at the current time, but f dot, that is the derivative of f with respect to time, is less than 0. That means if you move the time even by the smallest bit forward, then you will leave the plastic the yield surface. That means because f dot is less than 0, by a simple Taylor's expansion, f equal to some f at time t or delta t, f it is equal to f0 plus f dot, you know, delta t, f dot 0 delta t, you understand. So, if f dot is less than 0, this is less than 0, that means f delta t, however small delta t is, will become negative, because f0 is 0, okay, f0 is 0, we are originally on the yield surface at time t equal to 0. As soon as we move, it will leave that yield surface, and therefore the response will still be elastic. So, there are two conditions which are important. One is f strictly less than 0, it is elastic, and f equal to 0 and f dot less than 0, that is also elastic. Okay, but epsilon p dot, that is the plastic strain rate not equal to the 0 tensor, means that there is actually some plastic response. In such a case, what will happen? In such a case, f will be definitely equal to 0, but that is not enough, because earlier also we had f equal to 0 here, but so we need an additional condition on f dot. That means not only will f be equal to 0, but incrementally f must continue to be 0, that means f dot has to be equal to 0, you see. So, the requirement for the plastic response to occur, the plastic driving to take effect, is that f equal to 0 simultaneously alongside f dot equal to 0, right. So, if you combine all these, then it means that modulus of epsilon p dot times f dot is always 0. You see, irrespective of whether it is elastic or plastic, it is 0. In the elastic case, epsilon p dot is 0, so therefore this is 0. In the plastic case, epsilon p dot is not equal to 0, but f dot has to be equal to 0, right. So, therefore, this is always true. This is called the consistency condition in classical plasticity. So, basically, if you also now recall another thing, that if you just take a look at the basic idea of the plastic response essentially acting as a constraint on the elastic response to constrain the response on the yield surface, then it also means that this is also true, correct. E p dot, which is the derivative, time derivative of the accumulated plastic strain, or which is the same as modulus of epsilon p dot, okay, times f, that is the yield function, will always be equal to 0. If it is elastic response, then f is less than 0, which is not equal to 0, but epsilon p dot is 0. So, its multiplication with f is always 0 in the elastic case. In the plastic case, f equal to 0, but epsilon p dot is not equal to 0, but multiplying the two we get again 0. So, this is called the Kuhn-Tucker condition, right, the Kuhn-Tucker condition. So, you see how many such conditions we are getting: the consistency condition for one, the Kuhn-Tucker condition, the flow rule, okay, the directionality hypothesis, co-directionality hypothesis, right. Now, let us talk about how do we invert the flow rule in the von Mises case, right. Here the aim is to find epsilon p dot in terms of the stress sigma and the given strain rate epsilon dot. This is the total strain rate, it includes the elastic and plastic parts, right. It is as if it is being applied from outside, the strain rate, okay, it is like a forcing. So, given these two quantities, how to find the plastic strain rate? That is a major problem. This is basically inverting the von Mises flow rule. Now, to do that, we actually need to do a lot of tricks in classical plasticity. So, first note that we can write the time derivative of the yield function f like this. You remember that the yield function itself was modulus of sigma 0 minus y. So, just take the time derivative on both sides. So, f dot is the dot sum of both the terms, right, with a minus sign in between. Now, you know, assuming that the plastic flow direction is not changing direction with time. So, np dot is 0. Therefore, this term modulus of sigma 0 dot can be written as sigma 0 dot inner product with np, because np dot term is gone, right, and y dot is as it is, but y is actually a function of the accumulated plastic strain, the hardening variable alpha, which is the accumulated plastic strain, you remember. So, therefore, now in order to find y dot, let us use chain rule, that means differentiate y with respect to EP, this, call this quantity as h, it is called the hardening modulus, it is always greater than 0, all right, such that now apply the chain rule. So, that y dot is derivative of y with respect to EP times derivative of EP with respect to time, right. So, derivative of EP with respect to time is nothing but modulus of epsilon p dot. So, basically you have y dot is h, the hardening modulus, times epsilon p dot's norm or modulus. Okay. So, if we substitute this here in the expression for f dot, then we have this equation for f dot, you know, as written here very clearly, you can see that. Now, if you just combine the two terms properly by requiring that sigma 0, because it is deviatoric, it can only sigma 0 dot, because it is deviatoric, has to be driven only by the shear modulus. But the Lamé, among the Lamé, two Lamé constants in the context of isotropic elasticity under small deformation, the other Lamé constant kappa or lambda some people call, which is the bulk modulus, does not play a role because sigma 0 is perfectly deviatoric. So, therefore, we can write f dot is 2 mu epsilon dot colon n p, you can see here. Okay. So, that gives you the expression for the modulus of so this quantity. Okay. So, basically minus epsilon p dot also has to be there because it is epsilon dot e dot, the elastic part of the strain rate that drives the stress, the deviatoric stress, right. So, this is very clear, should be clear to you, this expression. Okay. So, therefore, I can actually just rearrange this so that this epsilon p dot here and epsilon p dot here can be clubbed together here, right, leaving the other term which is 2 mu n p colon epsilon dot, right. Now, remember that H is always generally, most generally it is greater than, I mean almost always greater than 0. 2 mu is always greater than 0 for elasticity, it is the shear modulus. So, therefore, 2 mu plus H is typically greater than 0. We will assume that 2 mu plus H is always greater than 0. Okay. Now, this is my expression. So, this is the expression that we need now in order to invert the flow rule, that is to find epsilon p dot. Towards this, define the stiffness ratio beta equals 2 mu divided by 2 mu plus H. You understand here, 2 mu appears here, 2 mu plus H appears here. So, the ratio of the two, all right. Now, let us consider 3 different cases, right. We can think of, as I told you some time back, this epsilon dot here, the total strain rate is something like a driving term. Think of it as a driving term. Okay. So, first, consider the case in which this epsilon dot inner product with the plastic flow direction n p is less than 0. Okay. So, if that is true, then what happens? Then this quantity is less than 0, right, the first term on f dot on the right hand side of f dot, but actually epsilon p dot suppose is greater than 0. Okay. Modulus of epsilon p dot suppose is greater than 0. In that case, this quantity is also negative, right, this quantity is both are negative. So, then what will happen? F dot has to be negative, but if f dot is negative, plastic flow cannot occur, that means epsilon p dot equal to 0, but this contradicts our assumption that epsilon p dot is not equal to 0, right. So, therefore, the only possible scenario in this case is that epsilon p dot equal to 0. Okay. Now, consider, so this is what is called the elastic unloading. Whenever NP inner product with epsilon dot is less than 0, it corresponds to elastic unloading. Now, consider case 2 in which we have NP inner product with epsilon dot is equal to 0, right. Now, again if you look at the expression for f dot here, the same thing here, then it means that the first term here is 0 because we assumed NP colon epsilon dot is 0. So, the second term can either be 0 or negative. It is negative if plastic flow is occurring, because epsilon p dot in that case modulus of it will be greater than 0, right. But if plastic flow is occurring, f dot cannot be less than 0, right. So, therefore, the only way in which a consistent solution can be arrived at here is that epsilon p dot must be equal to 0 even if f dot actually is equal to 0. So, here f dot equal to 0 right, but here epsilon p dot is also equal to 0. That means nothing is moving because there is no straining being applied, because we assume that np colon epsilon dot is 0, right. So, this is called the neutral loading condition, right. But the most important case is the third case, which is called the plastic loading, where the inner product of np and epsilon dot is greater than 0. In such case, you can clearly see from the expression for f dot again that the first term is greater than 0, but if the second term is actually equal to 0 because of the fact that epsilon p dot is 0, then f dot becomes greater than 0, which is inadmissible, because that will take, starting from f equal to 0, f dot greater than 0 means in the next time step f will be greater than 0, which is inadmissible, because the stresses cannot leave the yield surface, go beyond the yield surface. So, therefore, the only possibility that happens when np dot epsilon colon epsilon dot is greater than 0 is that the plastic flow must occur. Therefore, modulus of epsilon p dot must be greater than 0, okay, for f dot to be equal to 0, right. So, this is the plastic driving condition, correct. So, in this case it is very easy to see that epsilon p dot is nothing but this beta 2 mu by 2 mu plus h times the modulus, basically the inner product of epsilon dot in the direction of np, right, times np, right. This is my condition for, this is the inversion of the von Mises thing, leading to an expression for the plastic strain rate in terms of the applied strain rate, okay. Now, we have actually followed some of these, right. So, it is important for you to go through these lectures again and again to really understand what we have discussed. Maybe the first time you may have only understood half of it, but I can assure you if you go through it again and again, then slowly you will follow what I have been talking of so far. But the issues with this approach is that there are too many hypotheses. So, let us count them. One is the yield criterion, codirectionality hypothesis, flow rule. No, I have not written all of them. Then there are the consistency conditions, Kuhn-Tucker conditions, my God, so many, right. There does not seem to be any underlying variational principle. So, it does not look like a pretty elegant approach, is it? Not clear at all, therefore, is how to extend this approach, this particular logic, for example, to yield surfaces with corners, and yield surface where, you know, this kind of corners are there, right. So, this is the elastic zone. There are corners like this, these are the corners, right. These are points of non-smoothness, right. So, how do you extend this kind of logic to such corners? Such as, for example, the kind of corner, this kind of corners will appear in Tresca plasticity. So, convex analysis addresses many of these concerns. The most important thing is that convex analysis gives you an energy like term whose minimization would give you the plastic flow. What more can we ask for, right? So, better to move away and talk of a more futuristic, a more appropriate means of understanding plasticity even in the basic case. So, to do that, first we need to talk about what is a convex function, right. You may be already knowing that a convex function is basically a function phi. It is acting on any vector or function in the vector space or function space V and leading to, let us say, a real number, okay, including a possible value could be plus infinity, but not minus infinity in our case, okay. So, this is basically a scalar valued function of a vector or a tensor, okay. So, this kind of a function is convex if this condition is valid. That means it is something like this. Suppose this is the function, okay, this is my axis, right. So, if you draw take 2 points on this function, this and draw a chord, a line joining the two, then any point on this line must be above that function if it is convex, right. So, this is exactly what is stated here. This equation on the right for any lambda between 0 and 1 is nothing but the equation for this chord, right? Lambda phi x, this is my x and this is my y. So this is my x, so this is my x, this is my y actually, and this should be my phi y and this should be my phi x, okay, right? So you see that I have actually joined these 2 points phi x and phi y using a chord, and the equation of that chord is lambda phi x plus 1 minus lambda phi y. Well, lambda is between 0 and 1. If it is 0, then it will be phi x only. If it is 0, then it will be phi y. If it is 1, then it will be phi x. In between, it will be lying at points in between, right? So those set of points which are on this line has to be below the points on this graph of phi, which is on the left hand side, okay. So this is essentially the definition of a convex function. So convexity essentially is of a great use for us because it implies stability. You see, convex functions will have a well defined minimum. Basically all my solutions should therefore, if I do a variational principle based on a convex function by minimization of a convex function, then I should get a clear cut minimum or a infimum. So in other words, I will have a unique solution and the solution will be stable, because if I try to move away, then the energy will not permit me, okay, because the energy increases in those directions, and it is unique because there is only one such minimum, right, not two. For non-convex functions there will be multiple minima, right, but most importantly it means stability, you know. So that needs to be explained a little. So I will explain this and stop this talk. Let us say that I have a non-convex function of this type, right. So you see, if I take 2 points, one here and the other here, then in between if I draw a chord, it falls below, correct. So what is actually happening is that there is no stability if I move from this point to this point, because I am actually as if I am hill climbing, and that is not a stable operation. No, hill climbing, you can fall anytime because of gravity, right. Here the energy gradient will actually act like gravity and make you fall. So it is a very unstable thing to actually work with non-convex functions, right. Now therefore, you know, so we must understand therefore that convexity is what essentially is responsible for preventing runaway responses, and therefore it plays a very important role in the variational logic where we try to find a minimum, right. We should be able to do it in a stable manner, right, and there should be some uniqueness associated with it. So we, in the next talk we will be continuing with this this logic of convex analysis. We have already discussed the convex function, but what is most important in the convex analytic treatment of plasticity is the use of what is called the legend of Fenchel transform. So we must understand that properly in order to be able to use this variational logic, okay. So till then, goodbye and thank you for your attention.